Hello everyone, welcome to my presentation. In this presentation, I want to propose a new high step-down DC-DC converter suitable for the power supply to the server computers. So let me start my presentation. As you know, the widespread of the information technology is increasing power consumption in telecommunication infrastructure. And this increasing power burden on the infrastructures requires more efficient power supply system for the data centers. Here is a conventional AC power supply system to the data centers. The commercial AC power is supplied in the form of the AC power and delivered to each server computers in the form of the AC power. Afterwards, in each computer or in each server rack, the AC power is converted to the DC power, and afterwards, the power conversion stages is experiences to adjust the output voltage to much more smaller voltage to fed to the server computers. So in this type of system, we have many AC to DC or inverse conversion, and this lowers the energy efficiency and a heavy cooling burden. And of course, it results in a large converter volume. In order to mitigate this problem, a high voltage DC power supply system is proposed. In the system, the AC power is firstly converted to the DC power, and this high voltage DC power is supplied to each server computers or server rack. And in the server computers or server rack, has the high step-down DC-DC converters to output of small voltage suitable to fed to the server computers, and which operates the computers. So in this type of the structure, we have the less AC to DC or inverse conversion, and this results in higher energy efficiency and less cooling burden. And of course, we have small converter volume. But in this system, the important point is we have to install the high step-down DC-DC converters in the server computers or server racks. So compact a high step-down DC-DC converter is very important. So it will take an essential role for the widespread of the HVDC power supply system. In order to achieve the compact high step-down converters, many researchers have proposed that different type of the high step-down converter topologies. But these converter topologies are classified into two major categories. One is a topology with high step-down transformer. In this type of topologies utilize a transformer to achieve the high step-down ratio. This type of topologies generally have simple circuit network due to fewer circuit elements, but the transformer needs to be commonly utilizes this manganese zinc ferrite to make the transformer core, and it has a difficulty in high frequency operation more than 1 MHz. Therefore, this converter is operated with a lower frequency, and this results in the bulky magnetic or capacitor devices. So in order to mitigate this problem, another topology utilizes the voltage multipliers or switching capacitors to make the high step-down ratio. Here is one of the typical topology. So this type of topology has no transformer, and it enables high frequency operation higher than 1 MHz, and therefore we can downsize magnetic or capacitor volume. But as you can see here, the switching capacitors or voltage multiplier needs many circuit elements. This can actually hinder compact implementation. But high frequency operation is very effective for downsize the bulky magnetic or capacitor volume. So our research objective is to propose a new converter topologies which can achieve the high step-down ratio. Thereby, we can reduce the voltage multiplier stages. How to increase the step-down ratio? Beforehand, we have to analyze the problem of the conventional high step-down converters. Here's a typical step-down converter topologies with the switching capacitor stages. The switched capacitor divides the input voltage into by the number of the switched capacitor stages and generates the AC voltage. So the output is like here, and the amplitude from 0 is equal to the input voltage divided by the number of switched capacitor stages. And this output is decoupled with a filter, and the output is like here. So we can adjust the output voltage using the duty cycle. But our idea is to how about eliminate the DC element from this AC voltage by installing the capacitor. Here I install the capacitors is here. Then we have a pure AC output voltage like here. Then the output voltage amplitude from 0 to here is almost half. So this type of the topology, this one is called as a Cockcroft-Walton circuit in the bidirectional form. And then our idea is to feed to this output to the current up the rectifier. Then the output voltage is equal to here. So we have the very small output voltage. But of course, we have to adjust the output voltage by utilizing the duty cycle. So then, how about adjusting the output voltage of this Cockcroft-Walton circuit by to have this output waveforms? Then we can have this type of output voltage, and we can greatly reduce the output voltage. So our idea is Cockcroft-Walton circuit plus current double rectifier may achieve more high step-down ratio. Here is the proposed converter. This converter is formed with combining the switching capacitor circuit and current double rectifier as shown here. This converter has the 3 operating modes as shown here. The mode 1 is the switchiness A, and odd number switches is in the operating mode. On the other hand, in mode 3, the switch B and even number switches is in the operating mode. And in mode 2, only SA and SB is in the on state, while no switches in the on state in the switched capacitor circuit. So as a result, we have the voltage waveforms at here. The output of the switched capacitor circuit is like here, and we can adjust the duty ratio here by the duty cycles of this low side switch. Then this was fed to the current double rectifier. The current double rectifier have the 2 output current with the interleaved structures, so we can have the cancels out the current ripples in the output current. So we have the very small output current ripples with a very small inductance value of each 2 inductors. So this one is an analytical comparison of the conventional converter and the proposed converter. The topology is very similar, but the step-down ratio is entirely different. So this proposed converter can achieve almost half the output voltage with the same duty cycle. And then this one is comparison the number of parts. Actually, the proposed converter can have the additional 3 switches and additional 1 capacitors if we compare the same number of the switching capacitor stages. But of course, because we can achieve the more higher step-down ratio, and we can reduce the number of the switching capacitor stages. Then, if we reduce the switching capacitor stages, we can achieve the reduction of the number of the switches or capacitors. And of course, as inductors, we have the 2 inductors in this circuit. But as I have mentioned before, the current double rectifier achieves the interleaved output. Therefore, we can have the very small inductance for the inductors. So in total, a volume of this inductors can be expected to be smaller than the conventional one. The voltage rate of the state is almost the same, and the output current ripple As for the current ripples, with the proposal converter is small due to the interleaved output. So proposal converter can reduce the switching capacitor stages and also reduce the bulky inductor volume. Well, next I want to show you the experiment. The purpose of this experiment is to verify the operating principles. For this purpose, so we constructed the proposal converter with 3 switching capacitor stages. Here is the picture, and here is the operating waveforms. The red, pink, and red one is the voltage across the switch SA and SB respectively, operated with the input voltage 40 volt. So, but the voltage rates experienced by these 2 switches is much lower, only 6 volts. So voltage rate is far smaller than the input voltage. And next I want to show this one. So red and green line is the current of the 2 output inductors of the current of the rectifier. And as you can see here, the current is have the interleaved phase. So we can have the cancel out the current ripple as expected from the theory. So the operating waveforms were consistent with the theoretical expectations. Next, I want to show the duty cycle dependence of the output voltage shown here. The horizontal axis is the duty cycle of the low side switch, and the vertical axis is the output voltage. The dot is the experiment and theory, the line in the theory. So as you can see here, we have the very good agreement of the step-down ratio with the theory. And the next, this one is power conversion efficiency. The horizontal axis is output current. The vertical axis is efficiency. So this, as you can see here, this line and this line, everything is operated to achieve the very high step-down ratio. But even though we experienced the very good efficiency considering the very high step-down ratio operation. So theoretically expected high step-down operation was confirmed with good efficiency. Okay, so finally I want to explain about the conclusions. Well, the background is to develop the high step-down converters for HVDC power supply system. Our purpose is to propose a novel topologies which can achieve the less voltage multiplier stages for reducing the number of circuit elements. So our idea is combining the voltage multiplier with the current doubler rectifier as shown here, and this actually also implements the interleaved output to reduce the inductor volume. And the experiment showed that the performance is what I have expected from the theory. So as a result, we conclude that the proposed circuit is promising for constructing the HVDC power supply system. So that is all of my presentation. Thank you for your kind attention.